Hello, welcome to the cutting pattern video of the second series in the Introduction to the Easy Software System. In this section, a radial cutting pattern for the high-point membrane will be generated using the automatic method. We will demonstrate how the cutting pattern is aligned with the fabric width and how the orientation of the strips in the warp and weft directions can be optimized to ensure precision. For better illustration, the cutting process will be repeated several times, making the demonstration longer than strictly necessary in practice. Additionally, the process will highlight the option to ensure an exact match of the weld seam lengths between the connected parts. We are currently in the Static Analysis tab. Next to it are the tabs Cutting Pattern Generation and Automatic Cutting Pattern Generation. We now switch to the latter. All generated files are stored in the project directory. For better clarity, we create a new subdirectory specifically for the cutting pattern. To do this, there is a dedicated menu item, Auto Sub P, with the submenu Create Subdirectories Automatically. This opens a separate input window. For the cutting process, an EIN file and a DRE file are required. In our case, the default settings are already correct. By checking the box, the newly created directory is opened immediately. The process is then confirmed with OK. In the window header, we can now see the new path. Using the first tile form-finding data, the input data can be graphically reviewed once again. In the case of our high-point membrane, the primary structure is already missing. It was removed during the procedure of creating the subdirectory and is therefore no longer included in the file. As part of this process, both the surface triangles and the file were renamed. The names of the opened files are displayed in the window header of the GED editor. After closing the window, all preparatory tasks can be carried out by clicking on the first tile with the green arrow labeled Prepare Auto Cut. Now the parameters for the cutting pattern can be defined. By clicking on the central tile Strip Width Definition, a separate input window opens. For a radial cutting pattern, which is pre-selected automatically, it is recommended not to define the membrane width directly, but instead to specify the number of strips. Otherwise, it would not be possible to assign the same width to all elements. After activating the checkbox, Number of strips with identical width, we enter the value 20. The angle is then automatically adjusted. Finally, the input is confirmed with OK. The automatic cutting process can then be started via the fourth tile with the round green arrow, labeled Auto Cut Iteration. As the name suggests, this is an iterative process and should be carried out at least twice. During the first iteration, the input parameters are only roughly met. It is only from the second iteration onwards, by clicking the tile again, that the defined parameters are achieved with greater accuracy. We can now visualize the result graphically using the last tile, Easy Tailor. This module opens in a separate window where the cutting patterns are displayed. The X and Y directions define the material orientation. Due to the twisted cutting elements, however, these do not run towards the high point, meaning that the prestress in the installed state does not follow the fiber direction. To achieve a reorientation of the cutting strips, a specific parameter must be adjusted before the iterative calculation is carried out. For this, the Settings submenu is opened in the main shell within the menu Grown. In the newly opened window, the Parameters tab is selected and the checkbox for IYM is activated. By clicking the Apply plus Close button, the input is confirmed. The orientation of the cutting strips is now aligned along the angle bisector of the two boundary edges. The fiber alignment in the cutting pattern is now completed, and we can run the iterative cutting process again, executing it twice in succession. After the calculations are completed, the strip widths are listed in the information area. These are 2.57 meters, which does not match the required 1.72 meters. As a reminder from the first series, the width of 1.72 meters results from a material width of 1.8 meters. From this, 2 centimeters per side must be subtracted due to potential damage, plus an additional 2 centimeters per side for the weld seams. The calculation for the new number of strips is as follows. 2.57 meters times 20 strips equals 51.4 meters circumference. Dividing this by the desired width of 1.72 meters results in approximately 30 strips. Therefore, this must be adjusted in the settings via the central tile. By clicking this one, the parameter window opens again. Here we change the value from 20 to 30 strips and confirm the input with OK. We can then start the final iteration calculations, as usual, via clicking the tile with the green round arrow. After starting the calculation, the first iteration step is executed. Information about the calculation progress is displayed in the lower information area. It becomes clear that the strip widths are not yet fully adjusted. Therefore, additional steps are triggered by clicking again. With 4 iteration steps, each triggered by restarting the calculation, the desired state is reached in our case. The strip widths now differ by only a few micrometers. The final width is 1.723 meters. A tolerance of 3 millimeters compared to the target width results from the precise radial subdivision and is considered negligible for our cutting pattern. We can now display the flattened cutting patterns graphically and adjust additional tasks and properties for the final layout. This is done by clicking the last tile, Easy Tailor. As before, the program opens in a separate window. It now becomes clear that the elements have been realigned in the warp and weft directions, perfectly matching the requirements of the fiber orientations. The uniformity of the cutting elements is also clearly visible. For some cutting patterns, an exact match of the corresponding cutting edges is essential. For this purpose, the option Second Boundary Adjustment is available in the menu under Options. This ensures that in a second pass, the opposite cutting edges are further aligned with each other. Based on the biaxial tests and their evaluation, the compensation values in the warp and weft directions can be determined. These are entered in the Pre-Calculation tab. In our case, the X direction corresponds to the circumferential direction, where we want to align the weft thread. Therefore, under Compensation in X, we change the mode to non-constant TechNet, which reduces the compensation towards the edges and minimizes the elongation there. We set the compensation value to 2% and adjust the distance to total compensation to relative with 10%. The Y direction corresponds to the radial direction, along which the warp threads run. Here, under Compensation in Y, we simply change the value to 0.5%. We then adjust the seam allowance to 2 centimeters, since a total seam width of 4 centimeters is required. Once all inputs are completed, the changes must be recalculated. This is done by clicking Apply Changes and Recalculate and confirming the additional Attention pop-up window with Yes. All cutting patterns have been adjusted and can now be viewed individually by clicking on Cutting Pattern in the Quick Start toolbar. The seam allowances are also already included in the drawing. Using the black arrows, you can move to the next element. The blue frame represents the calculated strip area with the strip width consistently set to 1.72 meters as specified earlier. For quality control of the flattening process and the results derived from the calculations of the additional cutting preparation parameters, the relevant data are presented graphically and in report form under Cutting Patterns Overview. First, we check the report without compensation by comparing the surfaces in the 3D state, which is the original model, with those in the 2D state, the cutting pattern. The deviation amounts to 0.05%, which is considered satisfactory. In the report with compensation, the effect of the second adjustment option becomes visible. Here, the differences between the left and right cutting edges are compared and displayed. In this case, they are 0.0 millimeters. This confirms the precise alignment of the welding edges. At the end of the report, the surface differences are listed again. In our example, the difference amounts to 2.28%. After verifying all parameters, the final steps of the cutting process follows: the configuration and ultimately the export into a CAD system in DXF format. By clicking on the DXF Export button, the corresponding interface opens, where the settings can be edited and adjusted for the export. The first cutting part is displayed in CAD format. It includes the system line with compensation, the edge allowances, the welding marks, and the pattern labeling. Using the black arrows in the Quick Start toolbar, you can switch between the individual patterns. Another option is to display all patterns simultaneously. For this, in the control panel on the left side, go to the tab Export Parameters. And in the sub-menu File Name, File Type, Version, activate the checkbox, All Strips into a single file. For better visual distinction and for subsequent processing, the individual components can be assigned to different layers. This is managed in the Control Panel under the Layers tab. The detailed procedure for configuring the layers was already demonstrated in the video First Steps Easy Cutting Pattern and can be reviewed there if needed. Once all desired settings are completed, the DXF file can be generated via the right DXF button. Afterwards, the Easy Tailor window can be closed. This concludes the third video of the Second Steps Easy series, covering the cutting pattern of the high-point membrane. We hope we were able to give you further insights into the operation and the advantages of the modular Easy software system. In this series, we presented the mixed form finding of a high-point membrane with an integrated primary structure. Based on this, we performed a structural analysis and introduced the design process of the primary structure. By applying the partial safety factors and running an EC3 check, the load-bearing capacity was verified. In the cutting section, we demonstrated how easily, and in part even automatically, cutting patterns can be generated. Thank you for your attention. If you have any comments or questions regarding the procedure, please don't hesitate to share them here. We highly appreciate your feedback.